So the title of my talk is Lithium-ion batteries, the energy technology that changed the world. So who am I? Well, I graduated from SB College in 1965. So that was a few years ago. So this is how I looked. And now when I was there, I don't know if anyone of you remember me, but anyway, well, I'm very honored to be back to talk about lithium-ion batteries. In the 1970s, the idea of a rechargeable battery was considered as an impossible dream. But today, they are everywhere, and it is indispensable for our everyday life. And I've been able to make a small contribution to the founding and growth of this technology. And SB College education played an important role in my career. So this is what the outline of my talk. I want to talk a little bit about the lithium-ion battery chemistry and performance. We will go a little bit detail into the materials that are used in building a battery, anode materials or negative electrodes, cathode materials or positive electrodes, electrolytes, separator, and lithium. Then we will talk about lithium-ion battery state-of-the-art, where the technology is today. And followed by, I will spend a few minutes talking about very high energy density rechargeable batteries for electric vehicle and other large-scale applications of the future, followed by some conclusions. I know many of you are probably not very familiar with batteries, so I will provide a little tutorial at the beginning. So what is battery? A battery is an energy storage and conversion device. So a chemical energy is stored as anode and cathode materials in a sealed container together with the electrolyte and is converted into electrical energy. So it has two electrodes, which are two chemicals. Anode, the negative electrode material is oxidized to ions and electrode, and those ions and electrons combine with the cathode material to form a product C. So the overall reaction is you have two chemicals, an oxidizing agent and a reducing agent. They react to form a product plus a large amount of energy minus G, which is the free energy of the reaction. And that free energy is related to the electromotive force or the electrical potential of the cell through the reaction minus G is equal to NFE. And the potential E therefore is equal to the free energy change divided by NF, where N is the number of reactions involved in this reaction, a number of electrons involved in the reaction, and F is the Faraday constant. And E, the potential, is related to the current and resistance in a circuit. So you can use this relationship to calculate the potential of a chemical reaction, and therefore, and from that, the amount of current and the total charge that you can draw from that. So let me explain a little bit more what happens when you discharge a battery. Many of you are using your cell phones and computers right now, and you are drawing energy from the batteries in those devices. So what happens? Now, as I said, there are two chemicals here, an anode and a cathode. Those two chemicals will spontaneously react if you bring them together. We don't want to have that happen. So what we want to have is to have a controlled reaction. So how do we make these materials to react in a controlled fashion? So that's the key for a battery. So what we do is we first of all, let me say that the electrode reactions are redox processes, as we see in the previous slide. So they the reactions produce electrons and ions. So the key is to separate these two species. The electrons are separated from the ions through a separator here. A separator conducts ions but not electrons. Electrons are allowed to go through only through the external circuit. So that's how we control the reaction. And so we separate the electrons and ions. Their electrons are channeled through the external circuit and do work on the external load. You are able to use your cell phones and your computers, and the ions go from the anode to the cathode when you discharge your battery, and there they combine on the electrons come through the external channel, and the ions come through the electrolyte inside the cell. They combine to form the product. So that's just basically the reaction in a battery when you discharge the battery. And the reverse reactions happen in a rechargeable battery when you charge it. Can you see? What's the question? Oh, somebody's. All right. So this is just a little schematic here that a little animation showing what exactly happened. So as I said here before, the ions go from the anode on the right side to the cathode, and the electrons go through the external circuit, and this will continue until you fully discharge your battery, and the reverse happen on a charge. Just a little fun in the morning. All right, so this is so there are some properties of a battery that you have to remember. So this shows the discharge and charge behavior of a cell. What are we doing here? We are measuring the potential of the cell as we discharge it, take energy from it. So this is the fully charged state. The potential is at its maximum. So as you discharge, in this case, at a constant current, the potential decreases. So you are drawing current from it for a certain number of hours. Say in this case, 10 hours, you get 3 ampere hours. So you are discharging at 0.3 ampere. So you get 3 ampere hour. And when it comes to a potential when you don't get any more capacity from it, because if you continue to discharge, its potential will drop very drastically to 0 volt. You don't want to have that happen, so you stop it when the potential comes to a certain value in a given battery. In this particular case, you stop it around 1.5 volt, and then you recharge it, and so you continue charge and discharge like that. So what are the parameters that we need to remember? Capacity. Capacity is the current that you draw from the battery multiplied by the number of hours. So you get, so that's the current is measured in ampere, and the number of hours, so the capacity is ampere hour. And the energy, the total energy, is the product of the capacity and voltage of the cell. So in a cell like this, where the voltage is sloping, you take the middle, approximately the middle of the discharge curve. So in this case, you have you multiply by the middle about 2 volt, and the capacity 3 ampere hours, so you get 6 watt-hour from this battery. So those are the two parameters you have to remember. Then there is another property called energy density, which is basically watt-hour divided by the weight of the battery. So weight energy density is a watt-hour per kilogram, and you can also calculate volume energy density watt-hour per liter. So you just take the watt-hour from the battery and divide by the volume of the battery. So those are some of the properties of the battery that you have to remember. All right, so these are the main rechargeable lithium batteries that are commercially available today. Lead acid battery was the first rechargeable battery invented in 1859, followed by nickel cadmium battery in 1899. Lead acid battery is what we use for starting our cars. Nickel cadmium was the old battery that was used in portable devices. So then it took almost 100 years to come up with another battery, the nickel metal hydride battery, in 1992. And lithium battery, rechargeable lithium metal battery, was invented in 1976, and lithium ion in 1990. So you can see it has taken a long time for these batteries to be invented. First of all, let me say that these first three batteries are water-based electrolytes. So they are not very sensitive to air and moisture. Whereas these lithium batteries are very sensitive to air and moisture, because lithium is it reacts with the moisture or water. So you have to use non-aqueous electrolytes or organic-based electrolytes. So that's another difference between the traditional battery and the lithium batteries. And the other thing is because lithium is very reactive and moisture sensitive material, the battery has to be extremely tightly packaged and sealed. So there is a lot of engineering involved in it. Why it takes so long to produce new battery systems? Because new chemistry and materials, performance and safety, environmental issues, capital investments, and price. So this takes a long time, and it has taken a very long time because new chemistries had to be invented before new batteries were produced. Okay, so let's go and talk a little bit about rechargeable lithium batteries with a lithium metal anode. They were the first batteries of the lithium battery family. So the development started in the 1970s, and lithium is a very light metal. So it's also the most electropositive metal. That means that lithium can react with pretty much any material to produce a battery. Because thermodynamically, lithium should react with everything, but kinetics prevents it in some cases. But because it's also a light element, you are able to, it's very attractive for making batteries, because a high energy density batteries, because it produces, the weight of it is very, very light. So now it took another, a battery has two electrodes, negative electrode and positive electrode, or anode and cathode. So the key development in the development of a rechargeable lithium battery was the intercalation cathode. And the first intercalation cathode was the titanium disulfide, invented by Professor Whittingham in 1974, and he won the Nobel Prize for that last year. Well, then it also took a while to invent new liquid electrolytes, and so in the 1970s, soon after Professor Whittingham discovered the titanium disulfide intercalation cathode, people started fabricating a rechargeable lithium liquid electrolyte titanium disulfide battery. So this is the overall reaction in that battery. Titanium disulfide is reduced to an intercalated product, the lithium titanium disulfide, and on the anode you have the oxidation of lithium, as we saw in the earlier slide, and overall reaction is this. So, titanium disulfide. I'm sorry. Before that, let's see what intercalation electrodes are, because they are very important in the development of rechargeable batteries. So we need to take a look at what intercalation electrode reactions are. Titanium disulfide is a layered material with a two-dimensional lattice of sides. So you have here a schematic representation of the titanium disulfide lattice. So you have these TiS2 units stacked on one on top of each other like this, and with an interlattice spacing between the these titanium disulfide layers in the crystal. So, and those two interlattice bonding there is very weak. They are a van der Waals type weak bonding. So when you discharge your battery, or you insert the lithium into this interlattice spacing, that's what is called intercalation reaction. You intercalate the lithium ion into that interlattice spacing, and the electrons go into the conduction band in the material lattice structure. So you have really, in this case, a double injection of electrons and ions. And the beauty of this reaction is that it is very it doesn't cause much structural change in the material. The main thing that happens in the crystal lattice of this material is it expands and contracts this interlattice spacing a little bit. That's it. So that's why the reaction is highly reversible. You can insert lithium, extract lithium without too much structural change in the material. So another intercalation compound is graphite. We will come to graphite because this is an important material for lithium-ion batteries. It's the same reaction, intercalation reaction. Graphite has these C6 layers of carbon, 6 carbon atoms in a hexagonal unit to form this large sheets of C6 layers. So they are then stacked on top of each other, and then when you can insert lithium and extract lithium out of it. So it's another material. Another material is so this is an oxide, lithium cobalt oxide. It has the same kind of layered structure. We have here a CO6 octahedra. They are connected to each other through these lattice, the faces and corners of the octahedra, and then they are and those layers are then arranged one on top of each other. There are also materials with 1 and 3-dimensional lattice size. You see, in this case, it's a 2-dimensional lattice. So there are also materials with 1 and 3-dimensional lattice size. For example, in 1-dimensional, they are chains of these material of a material. They are then stacked together where you can insert and extract through these chain spacing. And there are also 3-dimensional lattice materials where you have either an octahedra or a hexagon or a cube, for example, with the lattice size sides through the faces of the cube or the hexagon. So this is sort of the beginning when I started working on it. As I said, there was already titanium disulfide known, but the lithium electrode was not cycling well. So our contribution mainly is in making the lithium anode work well with high efficiency. See, in the battery, you have to have both electrode work with the same kind of charge-discharge efficiency. So a lithium anode was not working at that time with good efficiency. In fact, it was not possible to charge and discharge a lithium anode more than a couple of times, or maybe 10 times. That was not good enough for making a practical battery. So what we did was we invented some new electrolytes, ether-based electrolytes. So this is a mixed electrolyte based on tetrahydrofuran and 2-methyl tetrahydrofuran with some small amounts of 2-methylfuran. And we were able to show that using that electrolyte and lithium hexafluoroarsenate at that time was the electrolyte salt, we were able to get, for the first time, batteries with more than 100 cycles. That was an exciting time at that time. So this shows the charge-discharge behavior of lithium titanium disulfide, full practical battery that we made. And in fact, I kept the original data sheet that I collected, the data that I collected on a chart paper at that time. So this is that original data that I collected. I still have it with me. So we also made following that we published these things. This was first published in an electrochemical society meeting in 1980. Then subsequently we published other papers. This is in this case we used a vanadium oxide cathode material. As I said, most people were working on cathode material. So there were several cathode materials available, but anode was the problem. So we made a significant improvement to that. So we were able to make other rechargeable lithium metal anode battery. However, we found that there was a problem in making the rechargeable lithium metal anode battery practical, because with the continued cycle, let's say after 100 cycles or so, the lithium anode, this is the electrode here on the right side, a negative electrode, completely fails. It's converted into a fine powdery material. So that was so you can get about 100 or 150 cycles depending upon the electrolyte that you use, but eventually it fails. And this powder material was also very reactive and can cause safety hazards in the battery. But if you look at this diagram here, you can see that the intercalation electrode remains intact. Yeah, although the lithium metal anode failed. So what do you do? What you have to do is to make a battery with two intercalation electrodes. So that's what lithium-ion batteries are. So lithium-ion batteries are batteries with two intercalation electrode. Intercalation electrode for the negative electrode and intercalation electrode for the positive electrode. So in the first commercial lithium-ion battery, graphite was used as the negative electrode because it has a potential that is very close to lithium metal. So you take a material with a low voltage for anode and high voltage for cathode. And at that time, Professor Goodenough came out with this material from his experience of using this for magnetic applications. So he came out with this material. So, but I show here a whole bunch of other materials on this potential scale versus lithium. So you can make lithium-ion batteries with many combinations of electrodes. However, you want to have two electrodes that a negative electrode that is the low, with a low voltage and a positive electrode with a high voltage, so you can get the highest voltage for the battery and also lightweight. So this is where the lithium-ion with the graphite lithium cobalt oxide battery that was commercialized by Sony in 1990. So it went away. The original lithium anode battery moved on to a lithium-ion battery where the negative electrode lithium metal was replaced by graphite, and the positive electrode a high voltage material, metal oxide, lithium cobalt oxide. So that batteries with intercalation anode and intercalation cathode materials gives long cycle life. So this is the detailed schematic of a lithium-ion cell. So it's a pretty complicated a device where you take your cobalt oxide as powder and very micron size powder. They are then bonded onto a current collector, and the graphite is also taken as this fine powder and bonded onto a copper current collector, and they are then so you make long sheets of this, about a foot long sheet of this in this particular original battery which Sony came out with, which is called an 18650 cell, which is a particular size cell, 18 millimeters diameter and 65 millimeters length, 18650. So this is the original Sony battery design. So you make these long sheets of anode and cathode, and have put a separator in between, and then wind it in the. If you are using a round can, you can wind it up and put it in the wound into the can, and put washers and gaskets and everything, and put a cap and seal it. So you get your. You can also cut them into smaller pieces and seal them in metallized plastic. This is the battery that you have in your cell phones. So that is a lithium-ion battery. Now, I don't know how much more time I have. How much more time I have? I have a lot more to present.
Yes, I can talk, sir, no problem.
Okay, I have. All right. So this is a graphite anode here. I want to talk a little bit about the chemistry of each of these electrodes here. That's very important. So as I said before, you have graphite anode. If you when you charge your battery, lithium goes into the interlattice spacing in the graphite structure, and you form a lithiated graphite. So that is what happens when you charge your battery. So you can study that. You can study that by separately by making a half cell with what we call a half cell with graphite electrode and a lithium counter electrode. So this is simply showing the electrochemical behavior of your graphite electrode. So as you can see here, this is the first charge of your graphite electrode. When you charge it first, you can see that there is this first part of it. There is some capacity here. This shows that the battery has capacity. This particular cell has capacity in this region because you have a reduction at a higher potential than 0 volt. Otherwise, it should just come down. It should come down to the graphite potential. I'm very close to 0 volt. I'm sorry. So anyway, so you have this part of the capacity which is called, which is the reduction of the electrolyte to form a film on the surface of the graphite. And that film formation is extremely important because that film protects the lithium, the graphite from reacting further with the electrolyte when you continue to cycle your battery. This is what we call a solid electrolyte interface on the graphite anode. So this formation of this is very important, and that depends upon the solvents that you use. So electrolyte composition extremely important for a stable graphite anode, because that you have to find an electrolyte that reduces to form an insoluble surface film that conduct ions. So it's there's a lot of organic chemistry and surface science and all involved in that. So you have to stable surface film on graphite called solid electrolyte interface, essential to prevent decomposition of the electrolyte. So that is the chemistry of the graphite anode. So the intercalation electrode, as I said, this is the first intercalation electrode, cobalt oxide. Subsequently, people came out with other materials. Lithium manganese oxide is a three-dimensional material. You can see the lattice sides. These are open holes in the three-dimensional lattice, so the lithium can go in and out of that when you discharge and charge your battery. Another material is this olivine lithium iron phosphate. There are many others. So this is the three materials that are now in commercial batteries. Lithium cobalt oxide. Now, cobalt is an expensive material, and it is also it's rare. It's mostly produced in some countries in Africa. They are always fighting there. So, and it is an expensive material. So there have been a lot of work to replace the cobalt in the cobalt oxide. And that is done by substituting some of the cobalt with manganese and nickel. So these material, nickel, cobalt, manganese, have the same structure as cobalt oxide. However, you have much less cobalt. This is what is the material that is in most commercial lithium ion, while this and that are becoming the most commercial battery electrode cathode material. Nickel, cobalt, aluminum, NCA, this is NMC. People are phasing this material out, although some batteries still have cobalt oxide. So these are the structures. So electrolyte is very important. There's a lot of organic chemistry. I don't want to, I had a good organic chemistry background from SB College. So I did organic chemistry was one of my favorite subjects. So I did a lot of work on electrolytes. So these are some of the electrolytes that we made. Others have worked on it too. So ethylene carbonate, a very important electrolyte. That this is the ethylene carbonate, dimethyl carbonate, ethyl methyl carbonate. Well, in a practical battery, a mixture of these three, 2 or 3 of these carbonate solvents are used to make the electrolyte for lithium-ion battery? Well, the reason for ethylene carbonate actually is a semi-solid at room temperature, because ethylene carbonate has a melting point of 37 degrees centigrade. So at room temperature, it's a solid. However, it's a very important solvent for lithium ion, because it is the solvent that forms the solid electrolyte interface that we talked about earlier. That happens from the reduction of the EC. So the first reduction, when you charge your battery, that is done in the factory. The ethylene carbonate is reduced to form a lithiated carbonate, organic carbonate material. That's an insoluble material that coat the graphite anode, and that is the SEI in the solid electrolyte interface material. So the use of ethylene carbonate is very important, but that is, that's a high melting liquid. So in order to dilute that, people put other carbonates, the low melting point carbonates like diethyl carbonate and ethyl methyl carbonate, because the battery has to operate over a wide temperature range. It has to operate from minus 20 degrees centigrade to 80 degrees centigrade. So you cannot just use one solvent, ethylene carbonate. You need to have find other solvents that will widen the temperature, operating temperature range of the battery. So you use a mixture of these solvents. So that's a proprietary thing. A lot of companies, they make all kinds of different solvents and mix them up, and there are also small amounts of additives they put in to improve the graphite surface properties, the SEI properties. So it's a very complex mixture that in these commercial batteries, and that's an area of research and investigation, very active even today. And the lithium salt, you need a salt, lithium salt along with the solvent to form the electrolyte. And the commercial batteries use a lithium hexafluorophosphate. It's a complex anion salt of lithium cation. So you form a Li plus PF6 minus. All right. Well, this shows that the band gap or the stability window of the electrolyte has to be better than be outside of the electrodes, because you don't want the electrolyte to reduce and oxidize when you charge and discharge your battery. So it's a very involved process to come out with a practical electrolyte. So that's why sometimes these the development of batteries take very long time. So this is I did some work early on to understand the structure of organic electrolytes. So this is this was a work I used NMR, nuclear magnetic resonance experiments to show that the lithium ions are solvated. That means in this case, it's a tetrahydrofuran and 2-methyl tetrahydrofuran. They form complexes with the lithium plus lithium cations. And so you have solvent-separated ion pairs here where the lithium is solvated. And we also showed through some temperature-dependent NMR studies that these solvents are all exchanging with the lithium ion continuously, so that when you have a mixed solvent electrolyte, you have a continuously exchanging solvents around the lithium ion to form this mixed solvent electrolyte, and they are we found them to provide a better low temperature performance, for example. So the structure of structural studies of the electrolyte is very important in explaining the and also to come out with new electrolytes for improved lithium-ion batteries. This is another electrolyte that we showed where the carbonate, which has both a carbonate moiety as well as an ether. So this methoxyethyl methyl carbonate has both, and we showed from NMR studies that the lithium is complexed with the carbonate part, preferentially to the ether, the side. Either component, the either part of the carbonate solvent. So those are some of the basic studies that you can carry out on the electrolyte. So we published these papers in 1986 and 99 in the Journal of the Electrochemical Society. So I also did some. So this shows what people do. So in order to, as I said, a battery has to work from very low temperatures to very high temperatures. So you look at the ionic conductivities of these electrolytes as a function of temperature. In this case, from minus 40 degrees to 80 degrees centigrade. And you can see that we did this study with the different mixed solvent electrolytes. Two salt, EC, EMC, EC, DMC, DEC. So it says EC, ethylene carbonate, dimethyl carbonate, ethyl methyl carbonate. And then another one where you made a 4 solvent mixture. So you can see that it has a good low temperature behavior, but all the way down to minus 40 degrees. Ionic conductivity is very important, for a battery, because that is determines the speed with which the ions move between the electrodes. So the higher the conductivity, the better it is. So this shows how new solvents are created to get both a low temperature and a high temperature behavior in batteries. And from these studies, I published, summarized many of these things are in this review paper that I wrote in 2015. It's in the Journal of Physical Chemistry. It's a pretty comprehensive paper. I can send it to you if you are interested, if anybody is interested. That where we, from studying the temperature versus conductivity behavior of this electrolyte, showed that the conductivity versus temperature behavior is non-Arrhenius, and from that we were able to show that the ionic motion or the ionic conduction is a solvent assisted property. In other words, the ions move in the battery through the by the assisted motion of the solvents because of the solvation of the lithium ion by the solvent. All right. So separators are important. I don't want to spend a lot of time here, but separators are two main materials are polyethylene and polypropylene membranes. They're very thin membranes, microporous material. So there are so there is some polymer chemistry also in this lithium-ion battery. So you have organic chemistry, liquid electrolyte, polymer chemistry, and so on. So you want to look for a separator with high porosity with small pore size for lithium-ion batteries too, because the higher the porosity, the better the conductivity, because the ions have to move through the the separator. The separator in the battery is soaked with the electrolyte. So it's they separate the two electrode, but there are very tiny micron size holes in there through which the ions can pass through. And the electrolyte is just put into the whole into the cell which gets into these electrode structures, the anode and the cathode porous structure, and into the pores of the separator. All right, so this is now finally we come to a full battery. So you have the anode and the cathode. You put together the graphite and the cobalt oxide in this case, and what the voltage you are measuring is simply the difference between the voltages of this is the fully charged battery, so it's around 4 volt, and then when you discharge the water, the voltage come down to and you stop it around 3 volt, because below that there is no capacity. This is simply showing the discharge of a lithium ion 18650 cell. This is the original Sony cell at different current. So you can, what happens when their design is such that in this particular case it gives almost the same capacity at 3 different currents. All right. So this is what the lithium-ion battery evolution. So this is in 1992, Sony, when they came out, this 18650 cell had about 1 ampere hour capacity. It gradually increased by 2004 or 2005. Just with the same electrodes, they were able to increase the capacity, double the capacity, more than double the capacity of the battery through electrode loading, cell engineering. Basically, most of the early improvement came from cell engineering. So there is a lot of engineering work in this, mechanical engineering or in this cell, how you fabricate your electrode, the loading on that, the weights of the current collectors and all that. So there is electrical engineering combined with mechanical engineering and chemical and engineering, as well as chemists. So it is a battery requires a little bit of knowledge in all of these different things. Or you have a group with who have expertise in all of these areas. So this is the 18650 cell today. This is the round 18650 size cell that is in your laptop, in the bigger laptops. The thin laptops use a flat cell, but that battery today has around the battery cell has around 3.6 ampere hour, and which is 285. Yeah, so it's some people claim they can make 4 ampere hour battery. So it goes. It's a slightly different for different manufacturers. So that is the state of the art. It took almost 30 years to reach, 25 years to reach this stage. So here is a summary of all of these, the various commercial batteries that are available. You have as I said, the cobalt oxide, the nickel, manganese cobalt oxide, the nickel cobalt aluminum oxide, and then there are also these iron phosphate and the spinel, or the lithium manganese oxide based battery cell. But the most portable electronics and electric vehicle, they're all made by with these the first three, or I should say the second and the third now, because people are moving away from cobalt oxide. The iron phosphate is it's a very good battery, but it has energy density is low, so it's used in some applications like power backup and load leveling and things like that. Utility applications where you don't need the energy density is not the key factor, but the ability to last long and cycle, give thousands of cycles, which the iron phosphate battery is able to do. All right, so this is just showing the capacity and cycle life. This is some data that I generated. You can set more than you can get a couple of thousand cycles now. And the battery, so you can charge and discharge some cases up to 2,000 cycles. So this is just showing what happens, when you operate your device at different temperatures. This is showing performance of this battery down to minus 20 degrees. This is at different currents. So you have some lowering of the voltage because of the increase in the battery resistance, but the capacity, you can run it fairly long time, even at lower temperatures or higher current, if you make the battery correctly. So in the commercial, some of these large manufacturers are able to do that. All right. So now, let's just go to electric vehicles. That is the next big thing are electric vehicle batteries. Electric vehicles and batteries for electric vehicles. 3 years ago, Indian Power Minister Piyush Gopal, I know politicians sometimes make big promises, but he said that by 2030, not a single petrol or diesel car should be sold in India. Well, the reason being pollution. See, if you look at the slide on the left side, this is taken from the Times of India publication showing people were wearing masks even before the coronavirus in Delhi for years. The reason is the pollution there in Delhi. You couldn't see. You see, you cannot see. This is during noontime. You cannot see the city at that sometime because of all the pollution, the discharge from the pollutant discharge from car exhaust. So in order to solve that problem, you need to come up with a car that use an alternative alternative energy. Of course, lithium-ion battery is an appropriate power source for that. And this is Tesla is they're one of the early developers of battery electric vehicle cars, but it's a very expensive sports car. Originally, they came from with it costs up to $100,000 dollars. Now they have a new car, Tesla Model 3, which is the 48,000 range, depending upon the size of the battery and the luxuries inside the car. So you get you can go in with this Tesla model about 200 to 250 miles on a single charge. 250 miles if you buy a 75 kilowatt hour battery. So it's a fairly large battery pack. You can see the battery pack is shown on the right side here. The battery is it's a very complex package. You have this, you make cells. The cells are put together to form modules, and then modules are then assembled into this large battery pack, and then put mounted at the bottom of the car here. So it's a lot of work goes into that, and the batteries are expensive. That's one downside of lithium-ion technology for electric vehicle. The price is still high, but they are coming down. as more and more batteries and more and more batteries are produced, factories are producing more battery materials, and they're also finding more materials, and materials are also recycled back to reuse. So there, with all that, the price is coming down. This is a Nissan Leaf. I think there is a, this is one, Nissan has some project in Kerala, and they are producing a Nissan vehicle with around 80 to 100 mile range. The small battery, smaller battery pack. So that goes about 100 to on a single charge, about 80 to 100 miles. So there is a lot of other companies are developing. As you can see, I have a, you don't really have to know all these things, but just a lot of companies are involved in developing various types of electric vehicle, and they are going to be here for in the many years in the future. And India is very much involved in it. I read that all the time. There are a lot of companies are beginning manufacturing lithium-ion batteries together with companies from China and Korea. So there's a lot of opportunities for future jobs and business and everything in this field. So this is increasing, accelerating very fast. So it is today lithium-ion market is 100 billion per year business, and it is expected to go significantly higher in the future. 100 billion is what? It's 10,000 crore, I guess. 10,000 crores, yes, something like that. Dollars. So another, there aerospace application of, I wanted to say a couple of, a little bit about that. The aerospace application of lithium-ion batteries, a very important application. They are used in airplanes now for various lighting and various kinds of utilities in the airplane. But a major success of lithium-ion batteries has been in the Mars exploration by Yadni. Lithium-ion battery was used in about 2003 time frame. I used to work as a consultant for Yadni Technical Products. So the two mission that was originally sent was the Spirit and Opportunity. They were very successful. I think the Opportunity vehicle lasted until 2018, almost 15 years. So that showed that lithium-ion batteries can be used in space for very, very long time. So this is a battery pack. I show this at the bottom of the slide here. All right. So what are the prospects for future higher energy density batteries? Well, with a lithium-ion intercalation electrode with one electron transfer per metal, lithium cobalt oxide was one lithium moving or one electron inserting and extracting from it. The maximum you can get is around 300 to 350 watt-hours per kilogram. So if you want to make super high energy density batteries greater than, say, around 350, you have to have a multi-electron transfer per metal. You have to transfer more than one electron per metal in a cathode material for an insertion electrode reaction. Or you have to find other kind of reactions, displacement type reactions where you transfer multi-electron processes. So you have multi-electron processes. So that's not a multi-electron transfer in a intercalation electrode or in a displacement reaction is not a simple thing. it's very often those are not very reversible processes. They are very often they are when you transfer one electron back and forth, try to do it reversibly, the electron gets stuck on one of the electrodes, and it doesn't want to get out of there. So it's not a it's a very involved research, and it's a lot of work, and a lot of ingenuity has to go into making super high energy density batteries in the future. There are a lot of people around the world is involved in research on that. So this shows the theoretical energy density for battery chemical couples. I made this diagram. Say lithium, as I said, is the most electropositive element. So lithium, you always want the lithium to be your anode because that is the most electropositive. And the best you can do, the highest energy density battery that you can make is to take lithium and fluorine as the. So you have fluorine as it's a gas as the anode, the cathode, and lithium as the anode. So if you make that, you can make the highest energy density battery. But of course, that's not possible because fluorine is a very reactive element, and it's also a gas. Well, the next best thing is a lithium oxygen battery. Because oxygen is, oxygen is a very safe material. We breathe it every day, so it's we are alive because of oxygen. So it gives 50 to 100 watt-hours per kilogram. This is just the energy density for just the materials in that. I'm not taking all the inert materials in this calculation. This is one way people compare materials. So lithium oxygen is the highest energy density battery that you can make based on the elements that are known in the periodic table. So this is a battery that I invented in 1996, which has around 5,200 batteries. So this is the ultimate battery. The lithium ion, for example, theoretical energy density is only in this region here. If you take lithium sulfur, that is a lithium and sulfur as the cathode is around 2,500. So a lot of people are working now on these lithium oxygen and lithium sulfur batteries, but they are not intercalation electrode. They are simple displacement type reaction or conversion reaction. So now I worked, one of the things that we did when I started out working as a young scientist many years ago was to work on a lithium sulfur battery. People are now reinventing that battery, but we published a paper on that many years ago in 1979, which was a long time ago, right? So, and we showed the cycle performance for that battery. However, this is charge and discharge arranged in a stack plot in a graph. However, it had many challenges here. The polysulfide that you form in the battery are insoluble and therefore limited cell capacity. There was some shuttle reactions. I don't want to get into explaining all these things because we don't have time. And poor lithium cycling efficiency. So this battery didn't really work, at least in our hands in those days. But people are kept on with it. There are still people working, a lot of people around the world are working on it today because this is one of the potential battery systems that can provide a significantly higher energy density. So there are a couple of companies that have come up with lithium sulfur battery packs for applications. This is a battery made by Scion Power. They use that for military application in drones. So some of these drones that are sent, used by the various militaries use a lithium sulfur rechargeable battery. And recently, their company in England, Oxy Power, the Oxys Power, they claim they have developed a rechargeable lithium sulfur battery. But we had given up on it years ago because of the problems. But I guess people kept on working, and they finally claim they have solved some of the problems. But I still have some doubts about a practical lithium sulfur battery. Now I come to the last section of my presentation, a short, another 10 minutes maybe. Lithium air battery. This is I invented and I patented it in 1996, and I published this paper, which has received more than 2,000 citations. If you go to Google Scholar, you can see that. So there are thousands of papers have been published after my paper. So it is the advantages are air is free, environmentally friendly. You can make both primary and secondary batteries, and can make it. The original battery that I made was a polymer electrolyte based battery. That's another kind of electrolyte. Instead of liquid, you have polymer. I mean, that's we did a lot of work on that. I don't want to get into that right at the moment, but we. When we made that battery, we made this is the how it looks like. This is a polymer cell packaged in polyethylene, metallized polyethylene pouches. So you have the little opening here, the electrodes are inside, and when you expose this thing to the air, the battery discharges. This is my original data that I published. So you can see that the battery, this is taking the oxygen from the air, and you can also charge and discharge it. And I did these calculations based on, there's a story behind it because it was an accidental discovery. So I made some calculations on what was going on, and I came up with the idea that it was a lithium oxygen battery system based on thermodynamics. So we did a lot of more recently at Northeastern University. This is in that paper I also published the data for magnesium battery, which was published separately, and I also did calculations for potentially useful other battery systems based on oxygen. So these are for lithium oxygen, aluminum. So these are some of the numbers that I have in that original paper published in 1996. So we did a lot of work in the last 10 years or so at Northeastern with my students. We did a lot of mechanistic studies of, we published some very nice papers in Journal of Physical Chemistry and Electrochemical Society journals. And we did oxygen reduction reactions in oxygen reduction reactions in non-aqueous electrolytes like ethers and carbonates and all that. And we came out with these main main conclusions for the mechanism and products that are formed, the factors that influence the products and products in an oxygen battery or an air battery. Lewis acidity of the cation of conducting salts, Lewis basicity of the solvent through solvation, ion pairing effect of the anion with lithium, and catalysis is also very important. So if you can look at these papers here, or maybe I can talk to you some other day. So this is the overall general the mechanistic scheme for the reduction of oxygen in a non-aqueous electrolyte. First step is a one electron reduction to form a superoxide that complexes with the lithium, so it has some stability, and the stability depends upon the solvent that you have, and then it is either chemically decomposes to form peroxide or it is reduced further. You can reduce it further if it stays long enough in the electrode. which happens with certain electrolytes. So, and the stable product in all solvents is the peroxide. And we developed this hard-soft acid-base concept to explain these things. So the lithium, you can always, finally you form lithium monoxide as the final product. And we developed several electrolytes, sulfones and sulfoxides, and we permit glycol dimethyl ethers, these are ethers, and then ionic liquids, another class of compounds. So we did some a lot of electrochemistry, battery discharge, and looked at the discharge products through analytical chemistry using X-ray, energy dispersive X-ray spectroscopy, and X-ray diffraction patterns, and chemical analysis showed that the reaction is this. The lithium, when you discharge your battery, you reduce your oxygen to lithium peroxide, and you can charge the battery as well. You can charge and discharge it if you use a catalyst. So why there is a lot of interest in that, because you can significantly reduce the size of the your device when you go from a conventional. This is a primary battery they use in some military applications. When you go from the traditional primary battery to a lithium air, you can almost reduce the size of that battery half. So that's a big advantage. So that is my presentation here. Lithium-ion batteries have changed the world, and I have been able to play a small role in this technology revolution. So the science of it involves chemistry, chemical engineering, electrical engineering, mechanics. So it involves a lot of different areas of science and engineering, and therefore you can have a rewarding career in a battery science and engineering. And the energy density of battery, a lithium-ion battery today is around 300 watt-hours per kilogram, or 750 watt-hours per liter. And we are approaching the limit of 1 electron per metal capacity in this. So, electric vehicles have been made possible because of lithium-ion batteries, and that will be a major next generation transportation mode for people on this earth. So new cathode materials with multi-electrons per metal are needed to develop batteries with an ultra-high energy density battery. So that will be the area that people have to work on to develop new batteries. So, and two battery systems that people are working on are lithium sulfur and lithium air batteries. All right, thank you very much.